Very good morning. I am Dr. Shuchandra Banerjee, and today is the introductory lecture for the subject Computer Organization and Architecture. Computer Organization and Architecture is a very important subject for the CSE students and its allied branches for core knowledge, at the same time for performing well in various competitive examinations. So let's start with the subject now. Now, coming to the name of the subject, the name is divided into two parts: computer organization and architecture. So, what is computer organization and what is computer architecture and how they differ from each other? Let's study that. So, computer organization is mainly concerned with the way the hardware components are connected together to form the computer system. So, in computer organization, we mainly deal with the various physical components such as the signals, the interconnections, and the circuits which are necessary for the computer. Whereas in computer architecture, we study about the behavior of the various functional modules which are connected together to form the computer system. To be more brief, in computer organization, we study how the computer does anything, and in computer architecture, we study what the computer does. So, this is a brief introduction about what is computer organization and what is computer architecture. Now, let's come to the topic: what is digital computer? A digital computer is a digital system that performs various computational tasks. So, what is the main task of a computer? That whatever instruction we give to the computer performs it inside and then gives us the result. Now, from where this word digital came, or what does it word digital imply? The word digital implies that the information in the computer is represented by variables which take limited values, limited number of discrete values, which is 0 and 1, which we call as binary values. So a binary digit is called a bit in case of digital computers. So it takes only two values, 0 and 1. So this is the main concept for the digital computer. Now let's come to the various parts of the functional entities of a digital computer. It comprises of the two parts, the hardware and the software. Now what does this hardware means? Hardware comprises of the various electronic components and the electromechanical devices which together build up the system. For example, the central processing unit, the main memory, the input output devices together make up the hardware of your computer. Now, what is the software? Now, software means it consists of the instructions and the data which the computer manipulates to perform various processing tasks. Now, software can be again of two types here. It could be system software or it could be application software. Now, what is system software? A system software can be considered to be a part of the hardware of the system, in the sense that the system software is a very specific is a set of programs which are responsible for making a perfect usage of the various hardware components of the system. One such example of the system software is the operating system. What are the various kinds of operating system that we'll be studying in later on in this slide itself? Okay. So system for the time being, please remember that system software is a specific set of programs which are responsible for maintaining the hardware or helping the user, or it is an interface which acts between the user of the computer and the hardware so that the hardware is utilized at the most. Now, what are application softwares? Application softwares, on the other hand, they are the specific programs for doing specific tasks. For example, Word. Word is an example. Microsoft Word is an example of application software which is mainly used for text editing, mainly, or writing down anything. Now let's come to the von Neumann architecture. Von Neumann architecture was being proposed by a scientist called von Neumann in the year 1945. So according to the figure, as you can see, this is the basic architecture of a digital computer as given by von Neumann. So von Neumann architecture comprises of the two parts, the control unit, the central processing unit, which comprises of two parts, the control unit and the arithmetic logic unit. And it also comprises of the memory unit and the various input output devices. Now what is the central processing unit responsible for? The arithmetic logic unit of the central processing unit part is mainly responsible for performing various arithmetic and the logical operations. For example, addition, subtraction, multiplication, division, the logical and, or not. So various logical operation as well as arithmetic operations needed by the various computational tasks are being performed by the arithmetic logic unit. Now what is this control unit mainly responsible for? The control unit is responsible for generating various timing and control signals. So the control unit is responsible for generating various timing and control signals necessary necessary to necessary for the computer system to operate. Okay, so obviously there are certain operations which need to be performed according to certain time. So a given clock with a certain clock pulse, so a few number of operations need to be performed. So this all everything is being controlled by the control unit. So you can consider the control unit to be the for human beings, the brain of the computer is a control unit who is mainly responsible for if responsible for how we move our hands, how we move our legs. So control unit is something like that which is responsible for controlling the various operations of the computer. Now here one more thing I want to add here is that there could apart from the memory unit, here the main memory unit means the random access memory or the main memory of your system. Okay, so the main memory of your system is the place where the programs or the instructions are brought into the system, so that then only the system can execute. So the main memory is responsible for storing all those things which are responsible to run your system. Now, apart from the main memory, the CPU also contain small storage locations which are known as the registers. Now, what are these registers? Now, registers are the small units or small memory units which are placed inside the CPU, and it is responsible for storing those intermediate results when the computer is performing any arithmetic or logical operation. So there can be various kinds of registers. We will be having a detailed discussion on register in later on in our lectures. But for the time being, let's learn about one or two registers. One could be the accumulator, the other one could be program counter. So what is this program counter responsible for? Program counter is responsible for storing the address of the next instruction to be executed. At the same time, the arithmetic logic unit, at the same time the accumulator is responsible for storing the intermediate results for any arithmetic or logical operation. So this was being proposed by, and apart from this, one more thing which von Neumann proposed was that it was also known as the mm, stored program concept. Von Neumann proposed the stored program concept. According to von Neumann, the instruction and the data on which the operations need to be performed are stored in the main memory of your system. Okay, so to get all the instruction and data needs to be brought into the main memory of your system for execution. So this was the concept which was being proposed by von Neumann. According to uh, him, the stored program concept means that the data and the instructions together lie in the main memory of the system. Okay, they are having the same locations. Okay, but in case of Harvard architecture, they could be stored in some other location. So that was being proposed by Harvard. Now we had already discussed in our previous slide about the system software. Now let's give a small idea about the types of system software the types of operating system which normally are being used in the computer systems. So to start with the first one, the first one is the batch operating system. The batch operating system, as from the name you can understand, is that the jobs are were being this was a very primitive technique, or a very primitive operating system in which the user used to submit the job to the system. There obviously used to be a human being who used to take care of these batches of jobs. That person was doing what? That person used to sort the jobs according to their similarity. So they would be keeping those similar jobs in batches, and those batch of jobs were being submitted to the CPU for execution. Now, what was the drawback of the batch operating system was the CPU utilization was very low. The CPU utilization was very low. So the reason the reason for this is that because they were submitted in batches, until and unless one batch of job was not completed, the CPU could not be given to the other batch of job which would be doing other jobs, or which would be doing other tasks. Okay, so the CPU utilization is very low. So in those days, the batch operating system, normally punch cards were being used. Okay, so something called punch cards were being used. The punch cards were being used the punch cards were being used to give the job to the CPU. Now this punch card had small holes. Okay, now if the light passes through this hole, then it could be considered to be a binary 1, and if the light doesn't pass, then in those cases it would be considered to be a binary 0. So in this way the data was being put in punch cards, submitted in batches, and the CPU would be processing it. Now even if one batch of job is requiring input output, the CPU won't be released. It would continue till one batch of job is finished. Next, let's come to the multi-programming operating system. In multi-programming operating system, so what is here came the concept of a number of programs could be loaded into the main memory of the system, and accordingly they would be given to the CPU. Okay, now suppose the jobs are be given in this order: first P3, then P2, then P1. Okay, so P3 would be the first job which would be executed by the CPU, and until and unless P3 completes, P2 won't be given the job. You would be asking like, then what is a usefulness? How the CPU utilization was increased in this case, rather than the batch operating system. Suppose P3 requires any IO interaction. Okay, so if suppose P3 requires any IO interaction, in that case, the P3 would be removed from the queue, and the next job would be given to, for example, P2 in this case would be given to CPU for utilization, for execution. So while one process is doing IO, in that time the CPU could be given the job. So in that way, the CPU utilization was increased. But here also one drawback is there. So suppose P3 doesn't require any IO. So in that case, what would happen? The P3 would P2 would keep waiting, even if suppose if P2 is a 15-second job, and P3 is a 1 hour job. In that case, the P3 would keep executing until and unless it finishes its job, even though P2 is a smaller time span job. So from here came the concept of the multitasking operating system, or which is also known as the time sharing system. Which is also known as the time sharing system. Now, what is this time sharing system? Each job would be allocated a certain time quantum to operate. For example, for each job it is given 2 seconds. Suppose P1 is also given 2 seconds, P2 given 2 seconds. A small time quantum is allocated to all the processes. So for example, P3 allocates gets the CPU for 2 seconds, it executes a part of the job. Then next, the CPU is being context transferred to the next job, which is P2. That again executes for 2 seconds. When this time quantum expires, then the CPU is given to the P1 again. So in this way, a certain time quantum was being given to each job, so that none of the job keeps waiting for a very long time. Next came the concept of the multiprocessing operating system. Here what we noticed is that in the previous cases that we were having only one processing unit. In case of multiprocessing OS, we had a number of processors. So if you have a number of processors, in that case, what we can do? So in case of multiprocessing operating system, what we do? We had a number of processing units, and the jobs could be given to these processors, so that they can be executed in a faster manner. So this is an example of the multiprocessing. So how does it differ from the previous one? Previous one was having only one CPU. In this case, we can have a number of processing units. We can have a number of processing units. Next is the real-time operating system. A very apt example of real-time operating system could be, for example, in case of missile launchers or in aircraft simulation. So these things, they are depending on the time. So such kinds of operating systems are known as the real-time operating system, where time factor is very important. Initially, the previous operating systems, it would take long hours to process the result, but in this case, the real-time operating system, it is very much time dependent. Next is the distributed operating system. In case of distributed operating system, the number of independent systems would lie in geographically distinct locations, and they would be connected via a network. They would be connected via a network, and this is how the distributed system operates. So number of standalone systems connected via standalone system, which are lying in distinct geographical locations, and they are connected via network. So this is what distributed OS is. Next is the embedded OS. Embedded OS is these kind of operating systems are mainly used in, for example, microwaves. Okay, so they are responsible for doing only specific tasks. Now, because we are talking now, let's come to the next topic, which is the logic gate. So we had discussed about the system software. Now let's come how to build the hardware. So logic gates are a very integral part of the for the subject computer organization. From the point of view is that because they are the basic building blocks of any electronic circuit, because a computer is an electronic device, and there are various circuits which are being integrated into it, and these circuits are built up using these functional modules, or very functional building blocks, which are known as the logic gates. So the various kinds of logic gates are AND gate, OR gate, NOT gate, NAND gate, NOR gate, and XOR gate. Now what is an AND gate? AND gate looks, the graphic symbol looks something like this. So if we have two inputs, suppose A and B, and only one output called F. So how do we realize this function F with respect to this input A and B? So that could be written so as F equal to A dot B, or this is known as the logical AND operation. Okay, so this is a truth table. The truth table the truth table depicts the various possible combinations of input, and what are the possible output for those combination of inputs. So for example, if I apply 0 0 to this AND gate, I get as output 0. So similarly, if I get 0 1, I get output 0. Similarly, 1 0 gives an output 0, and if it is 1 1, then I get an output as 1. So only when both the inputs are 1, I get as output 1 in the case of AND gate. Similarly, for the case of OR gate, an OR gate looks something, so graphically it is represented in this manner. So the algebraic function for the OR gate is a f equal to a plus b. So where the plus sign denotes the logical OR operation. Now what is the truth table? The truth table is according to, again, the same possible combination. The two possible binary values which can be applied to this logic gates are 0 0 0 1 1 0 and 1 1, because if there are two inputs, number of possible combinations we know it is 2 to the power n, or 2 square, because the two inputs, so we get four possible combinations, which is these are the various possible combinations. So but in case of OR gate, what we find is that if any one of the input is 1, we get as output is 1, and also if both the input are 1, we get output as 1. So this is known as the this is a truth table for the, this is how the function operates if we give these possible combinations. Next we get the NOT gate. Now NOT gate is also known as the inverter. So whatever we give as input in A, that would be inverted. So if I give 0 as input, what do I get as output? I get output as 1. Similarly, if I give 1 as input, I get output as 0. So this is what the concept of the NOT gate. Now let's come to the NAND gate. A NAND gate is nothing but an AND with a NOT in the front. Okay, so whatever we give as input, that is being inverted. So if I, because the output of the AND gate is A dot B, so because of this inverter in the front of the NAND gate, it gets complemented. Okay, so A dot B bar. So here could be there is a concept given by De Morgan, which is A dot B bar could be expressed as A bar plus B bar. Okay, so see, if I give two possible inputs in these combinations, which is 0 0 0 1 1 0 and 1 1. So if I get give 0 as input to A, so 0 bar plus 0 bar. So 0 bar is obviously, so I get as output, so I get as output as 1. So similarly for 0 1, also I get the output as 1. For 1 0, I get the output as 1. And when both are 1, when both the values of A and B are 1, 1 complement plus 1 complement, that gives output as 0. So this is what the truth table of NAND gate gives. Next, let's come to the NOR gate. NOR gate is again what? It is the OR gate and with an inverted value. So what we write, the output of the OR gate is what? A bar B, A is A or B, and then we give a complement sign. So this could be equivalent to, according to De Morgan, A bar multiplied by B bar. Okay, so see, if we give 0 0 as input, we get output as 1, because both complemented, so 1 into 1, it gives the output as 1. If it is 0 1, then it is output 0, and if it is 1 0, we get output as 0, and when both are 1, we get output as 0. Similarly, XOR gate. XOR gate, a XOR gate is looks like this, or rather, it is represented in this way. So, how does a logic function of a XOR gate look like? F equal to A XOR B, which could be expanded in this way: A B bar plus A bar B. So, based on the combinations of the A and B values given as the input, we get this value as the in the truth table. So these are the basic functions of the, this is how the logic gates operate, or how they function. Now let's come to the two types of circuits mainly we find in case here. So two types of circuit are combinational and sequential circuit. Now what is a, let's come to what is a combination circuit. A combinational circuit is a connected arrangement of logic gates with a set of inputs and outputs. So if I have n set of input and m set of outputs, I could express m in terms of the function, in terms of n input value. So what is a combination circuit? It is a circuit which is mainly composed of logic gates with suppose n set of input and we get m set of output. At any given time, the binary values or output of the function is a binary combination of the input. So how do we identify combination circuit? Let's take an example. One example of a combinational circuit is a half adder. So this is a circuit diagram of a half adder which comprises of a circuit which I discussed a few moments earlier. So I give two inputs a, x and y, and I have one output s, which is the sum, and the two inputs are fed into a AND gate from where I get the carry. So whenever the output is 0 0, so 0 0, the sum is 0 and the carry is also 0, because do you remember the what is a logic function? We had written a b bar plus a bar b. So this is how the logic of the XOR gate works. So here it is x and y rather than a and b. So whenever we provide the inputs in this manner, the result which we get in the sum and the carry are, so for 0 0 we get sum 0 carry 0, for 0 1 we get a sum 1 carry 0, for 1 0 we get a sum 1 carry 0, and for 1 1 we get a carry 1 and sum as 0. So this is a very small example of a combinational circuit. Next, what is a sequential circuit? So in the previous case, what we learned that in a combinational circuit, the output was always depending on the only the inputs which are applied. Now in case of sequential circuit, what we find, there is a certain memory element present in case of sequential circuit. So the output not only depends on the input but also the output on the for the past output. Okay, so which was being stored in this memory element. So it depends on the present input as well as the past outputs of the circuit. So this is why it is known as a sequential circuit, which comprises of a memory element. Now sequential circuit can be two types: synchronous and asynchronous. Okay, now this is an example of asynchronous sequential circuit. A sequential circuit could be made a synchronous sequential circuit if I apply a clock. So when the memory element are triggered by a certain clock pulse, then it becomes a synchronous sequential circuit. One example of synchronous sequential circuit could be the memory, or it could be the control unit. So these are the various example of the synchronous sequential circuit. Now, obviously, because we are doing certain processing task by our computer, data representation is a very important part of our subject. Now, so the binary information in digital computers are stored in memory or the registers. So what is registers? Registers are the small memory unit which are present in the central processing unit of the system. And what are they responsible for? They are responsible for storing the intermediate results, or it could be the address of the next instruction to be executed. So as I discussed, so the registers are the small memory unit which are very fast, and mainly why they were being used, one more reason for why the registers were being used is that there was a huge speed mismatch between the processor and the memory unit. Okay, so the speed of the processor is very fast while the memory unit would be a bit less, as a result of which the instruction could not be executed, because what any program to be executed, obviously it is what it is a set of instructions which we are giving to the computer. So to execute fast, these registers were being used. So this binary information could be control information or the data. Now we will be discussing about how the numeric data are actually stored in the computer memory. So to study that, so let's first discuss about the number system. Now, what is a number system? We are so called very much accustomed with the decimal number system. The decimal numbers comprises of 10 digits from 0 to 9. Okay, and each digit has a weight which is of a power of 10. Hence, the base or radix of the decimal number system is 10. Why? Because it could be expressed using this 10 digits. Next is the binary. Binary comprises of two digits, which is 0 and 1. Every digit position has a weight which is a power of 2, and hence the base or radix of the binary system is 2. Now let's learn about the conversion. Now, okay, sorry. One more number system is the hexadecimal number system. Hexadecimal, from the name you can understand, it is represented using 16 different symbols where the base or radix is 16. Why? Because the hexadecimal numbers 0 to 9 are represented. Hexadecimal numbers 0 to 9 are represented as in binary. Fine. Next, 10 to 16, they are represented by the alphabets A, B, C, D, E, and F. Okay, so using this 16 different symbols, we can represent the hexadecimal number system. Now coming back to the conversion part. Now how can you convert from one number system to another? That we'll be learning right now. So let's consider the very first one is binary to decimal. So how do you represent a binary number? A binary number is represented in this way. So suppose 11100. So already we are representing any number with the help of this binary digits 0 and 1. Now how do you find out what is the decimal equivalent of this binary? Now to convert it, how we move from right to left, which is known as, this is known as the least significant bit, and the topmost or the leftmost is known as the MSB, or the most significant bit, and we assign weights to each of these bit values. For example, this is assigned a bit value 0, this is assigned a bit value 1, this is assigned a bit value 2, this is assigned a bit value, this is assigned a bit value 3, and this is assigned a bit value of 4. Now how to convert? For each bit value, so 2 to the, this is the 0th bit position, so 2 to the power 2 raised to the power 0 multiplied by the bit value in this position, so multiplied by 0. So 2 to the power 0 is 1, so 1 multiplied by 0 we get a 0. Next, what for this bit position, this is a bit position of 1, so 2 to the power 1 multiplied by this bit value which is 0, it gives you 0. Next we move in this way, so this is bit value 2, so it is calculated as 2 square multiplied by 1, so it gives you 4. Similarly, this bit value, this is 3, so 2 cube multiplied by 1, so it gives as 8 into 1, that is 8. Similarly, the most significant bit position is 4, so 2 raised to the power 4 multiplied by 1, it gives you 16. Now how do you calculate the corresponding result? So you you can find out a sum of all these results, so 0 plus 4 plus 8 plus 16, so we get as the result as 28. So this is the corresponding decimal of the binary value 11100. So this was a whole number. If suppose we had any decimal values, so in decimal values what we do, after the decimal value, the bit position are being marked as I told you earlier. So bit position is marked as b minus 1, b minus 2, up to b minus m. So if the binary value is 0.0101, the corresponding decimal is how to calculate it, that is equal to 0 into 2 to the power minus 1, because this bit value we consider to be, because this value we consider to be minus 1, this is minus 2, this is minus 3, and this is minus 4. So 0, the bit value in the bit value is 0 into 2 to the power minus 1, 1 into 2 to the power minus 2, 0 into 2 to the power minus 3, and 1 into 2 to the power minus 4. So what we get as a result, 0.3125. So this is a corresponding decimal value with for the binary value 0.0101. Now let's how to convert decimal to binary. So the integer part and the fractional parts are considered separately in this case. So for the integer part, what we do, we repeatedly divide the given number by 2 and so on, and go on accumulating the remainders until the numbers become 0. So, and we arrange the remainders in the reverse order. And for the fractional part, what we do? For the fractional part, we repeatedly multiply the given fraction by 2 and accumulate the integer part 0 or 1, whatever. And if the integer part is 1, we chop it off. And then we arrange the integer parts in the order in which they are obtained. This is a technique for conversion of decimal to binary. So how to understand that? Suppose our given decimal value is 10.625. So the integer part is 10 and the fractional part is 0.625. So for the integer part, we go on dividing the number by 2 until and unless we get a 0 at the end. So 2 fives are 10, the remainder is 0. 2 twos are 4, remainder is 1. 2 ones are 2, remainder is 0. 2 zeros are 1 and remainder is 1. So from we collect in this order from the bottommost to the top. So the corresponding decimal binary representation for the decimal value 10 is represented as 1010. For the fractional part, how do we calculate? 0.6 to 25, we go on multiplying by 2. So it gives us 1.250. So from here we chop off the integer part, which is 1. Similarly, and what we are left with? We are left with 0.250. Again, 0.250 we multiply by 2, we get 0.500. So from here we get a 0, and from and then again 0.500 is multiplied by 2, we get 1.0. So from here we get a value 1. Now we go on collecting from top to bottom, so that gives you 101. So 16.625 in decimal is represented as 1010.101 in binary. So this is how the conversion for decimal to binary happens. Next is binary to hexadecimal conversion. Now, for the integer part, what we do, we scan the binary number from the right to left and translate each group of 4 bits into corresponding hexadecimal digit. Why 4 bits? Because we know that the base or radix of hexadecimal numbers is 16. So 16 is expressed as 2 to the power 4. So group of 4 bits are considered for conversion. We add leading zeros if necessary in this case. For the fractional part, what we do? We scan the binary number from left to right and translate here initially. For the integer part, we are doing from right to left. And for the fractional part, what we are doing it from left to right. So we translate each group of 4 bits into corresponding hexadecimal numbers, the hexadecimal digits from left to right. So here in this case, we can add trailing zeros if necessary. Now let's take an example of how binary to hexadecimal happens. So this is suppose binary representation. As I told you earlier that because this is in whole integer part, what we do from right to left, from right to left we scan a group of 4 bits. Okay, so 4 bit, this is 4 bit, this is 4 bit. So 1011 it represents B. Okay, so 0100 it represents 4, and 0011 it represents C 3. So the corresponding hexadecimal of this binary value is B43 in hexadecimal. Similarly, 1010100001. So how do you get the value? You again scan from right to left, take a group of 4 bits, again take a group of 4 bits. So if we had, because we have only 2 bits here, what we can do, we can add leading zeros in this case. So we add 2 more zeros here. So this is representing 2, this is representing A, and this is representing 1. So this is 2A1 in hexadecimal. Similarly, if for the fractional part, what we do in this way. For one, after the decimal, what we do, we take a group of 4 bits from left to right. Initially we were doing from right to left, in this case we are doing left to right, yes. So group of 4 bits, so 1000, it represents 8, and in this case I can add a trailing 0, so it becomes 4. So in hexadecimal, that is equals to 0.84. Now the opposite, which is hexadecimal to binary. So we translate every hexadecimal digit into 4-bit binary equivalent. So that is equal to, for example, if 3A5 is our given hexadecimal value, so 3 is represented in 4 bits as 0011, A is represented as 1010, and 5 is represented as 0101. So this is the corresponding binary value for hexadecimal 3A5. Similarly, if it is 12.3D in hexadecimal, how do we represent that? For the integer part, what we do, we represent 1 as a group of 4 bits, which is 0001. 2 is represented as 0010, and for after the decimal, for the fractional part, 3 is represented as 0011, and D is represented as 1101. So this is how the hexadecimal to binary conversion takes place. Now, binary numbers can be again of two categories. It is signed numbers and unsigned numbers. Okay, so if we have an n-bit binary number, we represent it in this way, which we learned earlier in few of our slides. So there can be, for n possible n-bit binary number, there are 2 to the power n distinct combinations are possible. That is 0 to 2 to the power n minus 1. So for example, if n equal to 3, how many distinct combinations are possible? 8 distinct, because 2 cube is equals to 8. So what are the possible combinations? Are 000, 001, 010, and 011, and up to 111. So this is how we represent binary numbers. If n is equals to 8, then what are the range of numbers that can be represented? That is equals to 0 to 2 to the power 8 minus 1, that is equal to 255. Similarly, if n is equal to 60, the range of numbers are 65,535. So this is what unsigned binary numbers deals with. Next, let us discuss about the signed binary numbers. Signed binary numbers means, obviously we could have positive as well as negative numbers. Okay, so how do we represent this? How do we represent the negative sign? So there are 3 possible approaches in this case. There could be sign magnitude representation, there could be 1's complement representation, and there could be 2's complement representation. Now let's see what is this sign magnitude representation. So for an n-bit representation, the most significant bit indicates the sign. So if it is a positive number, the sign bit is always set to 0, and if it is a negative number, the sign bit is always set to 1. So the first bit or the MSB represents the sign bit, and all the remaining bits represent the magnitude. So if n minus 1 bits represent the magnitude of the number. Okay, so let's discuss about the 1's complement representation. The positive numbers are exactly the same as in sign magnitude. only the negative numbers are represented in one's complement form. Now, how this one's complement of the number is calculated? We complement every bit of the number, which means complement. Already we have learned about the inverter, the NOT gate. So if it is a 1, we get as input. We complement the bit to 0. If it is 0, then we give as 1. So 1 is converted to 0 and 0 is converted to 1. So the MSB will indicate the sign of the number. If it is 0, it means the sign bit is 0, then it is a positive number. And if it is sign bit is 1, it represents a negative value. Now, what are the range of numbers? Maximum number which can be represented by the ones complement form, that is 2 to the power n minus 1 minus 1, and the minimum is minus of 2 to the power n minus 1 minus 1. Now, what was the problem with this previous to number system is the ones complement and the sign magnitude representation. The problem is that there were two different representations for 0. So if it is 0, so in if it is a sign magnitude, if it is plus 0, obviously the sign bit is set to 0 and rest all bits are also, if it is 8-bit representation. Suppose I am considering an 8-bit representation for 0. So if it is plus 0, it is represented as 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, and 8. So 8 zeros. And it is if it is a negative 0 for sign magnitude, only the, this is for the sign magnitude. The most significant bit is set to 1. Rest all values are set to 0. Similarly, in the case of ones complement, what we learned that in ones complement, each whatever the value is in the sign magnitude, that bit value gets inverted. So in sign magnitude, so in ones complement, how is minus 0 represented as? Minus 0 is represented as 1 1 all bits, because this is a negative value, so the sign bit is set to 1 and rest all zeros are being inverted. So 0 complement is 1, so all ones. So this is how we represent minus 0 in one's complement representation. And one more thing what we learned, that in one's complement, the plus 0 is same as the sign magnitude values. So because there are two different representations of plus 0 and minus 0 for both one's complement and the sign magnitude, so there was certain problem which arise. So obviously we have to find a solution. So how that was being found out by the 2's complement method. In 2's complement method, the positive numbers are exactly the same as in sign magnitude. Only the negative numbers are represented in the 2's complement form. Now, how do we can calculate 2's complement? 2's complement of a number is calculated by 1's complement plus 1. Suppose if I want to represent 4, or rather minus 4. Okay. So minus 4, what is the value? So because this is a negative number, the the sign bit is set to 1, and 4 is represented as 1 0 0 and rest all 0. This is for the sign magnitude part. 7. So this is for the sign magnitude. If I represent the same number in one's complement form, what would happen? I would simply complement these values. Each the sign bit remains as it is. So only zeros are converted to 1. 0 0 0 is converted to 1. This becomes 0 and this becomes 1. Now this is the ones complement representation. Now if I have to calculate ones complement representation for minus 4. Now if I have to calculate same minus 4 in 2's complement, I simply do what? I add a 1 here. Okay, so 1 plus 1, 0, carry 1. 1 plus 1, 0, carry 1. And this is 1, 1, 1, 1. This is how you represent the 2's complement of a number. Now 2's complement of a number is simply 1's complement plus 1. Now if I Now, how the 2's complement added or had an advantage over the 1's complement or the sign magnitude is that 2's complement had the same representation for plus 0 and minus 0. So, how is plus 0? How was plus 0 represented in the sign magnitude? Sign magnitude plus 0 was being represented as all zeros, and minus 0 was represented as um, minus was represented as 1, and all are 0. So this was the um, sign magnitude representation. Similarly, for 1's complement, how do we represent minus 0? The sign bit is 1 and rest all are 1. Rest all bits are 1. Now how do you calculate the 2's complement of this value? We simply add a 1 as we learned earlier. So 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1 0 carry 1. So you go on continuing, you add zeros, one carry, one bit is that is discarded. So what we find, even it is minus 0, 2's complement is representing it in the same way as it is plus 0. So we don't have any differentiation. Two different representations are not found in the case of 2's complement form. So for that reason, the 2's complement representation was helpful. Thank you.